tutorial on heat and constant pressure calorimetry. First we'll start with the first law of thermodynamics, and that's essentially the law of conservation of energy. And that states that energy is neither created nor destroyed in a chemical reaction, or any other process for that matter. Energy can be gained from the environment or the surroundings, or lost from your system into the environment or surroundings. The law of conservation of energy is called that first law of thermodynamics. Now, processes can be endothermic or exothermic. Exothermic processes or reactions are going to release energy in the form of heat, that is, from your system and into your surroundings. For example, burning something, you're releasing a lot of heat. In this case, propane, if we burn it in the presence of oxygen, we form carbon dioxide and water vapor. And as written, we produce 2,220 kilojoules of heat, burning 1 mole of propane. Combustion of methane is also exothermic, but not as much so. 1 mole of methane, CH4, again reacting with oxygen to produce CO2 and water, only produces 890 kilojoules of heat, but still it's release of heat and therefore exothermic. These exothermic reactions generate specific amounts of heat, and that's because the potential energies of the products are lower than the potential energies for the reactants. Here's an example of a reaction profile where energy is the y-axis and progress of the reaction is the x-axis. And if you look at methane, they're reacting with oxygen. There's a little barrier there in blue with the arrow indicating the amount of energy needed to activate the forward reaction, with a total energy involved of 890 kilojoules, which is the difference in energy between the reactants and products. So you can see you're releasing a net of 890 kilojoules. Now, endothermic reactions are going to absorb energy in the form of heat. For example, if I react barium hydroxide octahydrate with ammonium chloride, I add 164 kilojoules of energy, and we get barium chloride, some water, and a little bit of ammonia gas. But it's endothermic, it's going to absorb heat from the surroundings. If a reaction is extremely endothermic, you could heat it with a Bunsen burner or a hot plate or something to supply that needed energy. If it's minimally endothermic, perhaps it can just get that heat energy from the surrounding room without additional heating, as in this case. But they absorb specific amounts of heat, and this is because the potential energies of the products are higher than the potential energies of the reactants. Here's another reaction profile for the barium hydroxide reacting with the ammonium chloride. And you can see that I need a lot of heat to get that reaction going forward, but the net difference is 164 kilojoules, which is the amount of energy that you're going to have to put in. Let's take a look at internal energy. Internal energy, symbolized by E, is all of the energy contained within a substance or a system. This function includes all forms of energy: kinetic, potential, gravitational, electromagnetic, electrical, anything else. So you can talk about internal energy in terms of the first law of thermodynamics. So a more mathematical way of looking at it is the internal energy is the sum of the heat flow and the work. So we can say the change in internal energy of a system can be based on how much heat is given off or absorbed, or how much work is done on or by the system. Now, heat or work going into the system from the surroundings is going to be positive. Heat or work flowing out of the system and released into the environment will be negative. And that's our sign convention here. Now, in our case, chemistry is commonly done in open beakers on a desktop at whatever the atmospheric pressure is. So, a lot of times we'll consider things done at constant pressure. When we do that, the pressures aren't going to change by small increments, so you could almost consider that constant pressure, which means that if the work done is pressure volume work and the pressure really doesn't change, or the volume for that matter doesn't change much, we can say that's approximately zero, and therefore the work term would just drop out, and the internal energy would be approximately equal to the enthalpy, which is the heat change at constant pressure, or Q sub P. And so enthalpy is defined as the heat at constant pressure, and if we're at constant pressure and that work term is approximately zero, we can say the change in internal energy is approximately equal to the enthalpy. Now, let's look at calorimetry. That's, for example, if you want to have a cheap calorimeter, sometimes you can use styrofoam cups with a lid, or you can purchase a more expensive container designed for calorimetry from a science supply company or something of that nature. But it's designed to be a good insulator and not lose much heat to the surroundings. Now, if you have an exothermic reaction performed in a calorimeter, the heat evolved by the reaction is going to be determined from the temperature rise of the solution. It's going to require a two-part calculation, however, because the amount of heat produced by the reaction will be the amount of heat absorbed by that solution, but you're going to lose some, and some heat might be transferred to that calorimeter, even if you design it to be a fairly effective insulator, or lost into the environment. So you're going to figure out how much heat was lost into the environment, plus the amount of heat absorbed by the solution, which we can directly measure, and that will give us the heat from the reaction. Depending on how effective your calorimeter is at not allowing heat to escape, that term may be more or less significant. Now, the amount of heat gained by the calorimeter, or in general lost and not gained by the solution, we'll call the heat capacity of the calorimeter, or the calorimeter constant. And we can certainly figure out what that is and apply that correction. The value of the calorimeter is constant by adding a specific amount of heat to the calorimeter and then measuring the temperature rise. And if we know the substance, therefore know the specific heat and everything about the system, we can predict what the temperature changes should be, and if they're different, that's going to allow us to know what the heat lost is. Before we do that, let's talk about some energy units, so how we're going to measure this heat. The SI unit, or International System of Units, unit for the energy is the joule. There's an older energy unit called the calorie, which is still in fairly common usage. So 4.184 joules is exactly equal to 1 calorie. 1 kilojoule is 1,000 joules. 1 kilocalorie is 1,000 calories, or that's equal to 1 food calorie. Food calories are capital C calories, where ordinary calories are lowercase c calories. So the calorie is defined as the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. The specific heat of a substance is the quantity of heat required to change the temperature of 1 gram of that substance by 1 degree Celsius. So the definition is very similar to that for the calorie, except calorie specifies water, where specific heat specifies any substance. So by definition, water would have a specific heat of exactly 1 calorie per gram degree Celsius, or it would be 4.184 joules per gram degree Celsius. Metals like lead have lower specific heats than water. Water actually has a pretty high specific heat, where lead or other metals are going to be pretty low. Lead is 0.128 joules per gram degree Celsius, which you see is significantly lower than that of water. Heat can be gained or lost by a substance and calculated using this equation, Q equals mc delta T, where Q is the heat, and it can have any energy unit, usually joules or calories, where m is the mass in grams, C is the specific heat, either in joules per gram degree Celsius or calories per gram degree Celsius, depending on the energy unit used for the heat, and delta T is the change in temperature in degrees Celsius. Let's calculate the amount of heat needed to raise the temperature of 200 grams of water by 10 degrees Celsius. So we're going to use our Q equals mc delta T, and we're just going to plug in the amounts. So Q is equal to the 200 grams times the specific heat of water, 4.184 joules per gram degree Celsius. That's a constant. Specific heat will change depending on what substance you're heating or cooling off. And then our 10 degree temperature increase, 0.0 degrees Celsius. Run that through the calculator, we'll get 8.37 times 10 to the third joules, or 8.37 kilojoules of heat needed. Let's look at a different example. Calculate the specific heat of a solid in joules per gram degree Celsius and in calories per gram degree Celsius. If 1638 joules are required to raise the temperature of 125 grams of the solid from 25 to 52.6 degrees Celsius. So our Q equals mc delta T again. Our delta T, 52.6 minus 25 degrees Celsius is 27.6 degrees Celsius. Now we should be able to solve for the specific heat C and plug everything in. So C equals Q divided by M and delta T. Plugging in 1638 joules divided by 125 grams and 27.6 degrees Celsius. We're going to get 0.475 joules per gram degree Celsius. That's the answer in joules. We'll need to convert to calories. We can do that two different ways. We can convert the energy we're given to calories and then rework the problem, or we can just convert the answer. It doesn't matter which. I've in this case chosen to just convert the answer. Since the only unit different is the energy, we can just do a simple energy conversion. 4.75 joules per gram degree Celsius times 1 calorie per 4.184 joules. And that's going to give me 0.113 calories per gram degree Celsius. Look at a different example. In this case, if we're adding heat to something, we'd be remiss to omit the fact that the calorimeter can lose heat to the surroundings or absorb heat itself. So let's say if we take 50 grams of hot water at 90 degrees Celsius and we add it to a calorimeter containing 50 grams of water at room temperature, meaning 24 degrees Celsius in this case, increasing that temperature to 36.5 degrees Celsius. Calculate the heat capacity of the calorimeter in joules per degree Celsius, realizing the heat capacity of water is 4.184 joules per gram degree Celsius. Now, if I were to add hot water to that 24 degrees Celsius water, if I lost no heat, the final temperature would be the average between the two temperatures, which would be 57. But it only made it at 36.5 degrees Celsius, which means the calorimeter is fairly inefficient in this case, but we've exaggerated that for effect here. And many calorimeters aren't that inefficient, but we'll work with it just to make the point. So we've lost a fair amount of heat in that. What you have to do is calculate the heat lost by the hot water, just a Q equals mc delta T. So there's our delta T. We're going to absolute value this so that we don't get a sign issue. 53.5 degrees Celsius temperature change. and plug that in for the heat lost. And since we're saying lost, that kind of accounts for the sign. So we got 50.00 grams times 4.184 joules per gram degree Celsius and 53.5 degrees Celsius. So we lost 11,200 joules. Then we're going to do the same thing, except we're going to calculate the heat gained by the room temperature water. Same deal, 36.5 minus 24.0 degrees Celsius, or 12.5 degrees Celsius. So we can see the temperature changed a lot more for the hot water versus the cool water. Calculating that with the same MC delta T, 50.00 grams times 4.184 joules per gram degree Celsius times 12.5 degrees Celsius. So the cold water only gained 2620 joules. The difference is the heat lost to the surroundings or absorbed by the calorimeter. So that heat lost to the calorimeter or the surroundings will be the difference in those two, which means we lost 8,600 joules of heat out of our system. Now, we take that amount that the heat lost to the surroundings and divide that by the temperature increase of the cold water. So 8,600 joules divided by 12.5 degrees Celsius will give us 690 joules per degree Celsius, and we call that our calorimeter constant. Again, we exaggerated the heat lost here for effect. Really, you'd want a calorimeter that insulated a little better than that. So let's take that same calorimeter, realizing it was fairly inefficient, but we'll work with it anyway, and say now we've got an exothermic reaction, so we're going to get a temperature increase, but it's going to be, instead of a temperature difference between the two reactants, they're going to react in the calorimeter, and the heat produced by the reaction will produce the temperature increase. So we got 50 milliliters of 1 molar HCl reacted with 50 milliliters of 1 molar sodium hydroxide, and the calorimeter is describing the previous problem, so we've got our calorimeter constant. Temperature rises from 24.0 to 30.1 degrees Celsius. How much heat is released? We're going to assume the solution has specific heat equal to water, and the density is also that of water, so 50 milliliters will become 50 grams. So the change in the temperature, 30.1 degrees Celsius minus 24 will be 6.1 degrees Celsius. But what we're going to have to do here is, instead of just Q equals MC delta T, we're going to add back the heat loss to the surroundings, so it'll be the calorimeter constant times the delta T added to the MC delta T. So Q equals 100 grams times 4.184 times 6.1 degrees Celsius plus 690 joules per degree Celsius times 6.1 degrees Celsius. So we're adding in that heat loss term. We find that the reaction produced 6,700 joules of heat. Now let's look at a different example. Here is a common way of determining the heat lost and gained, and use that to determine the specific heat of a unknown metal. In this case, we'll determine lead. So 11 grams of hot lead metal, 100 degrees Celsius, is poured into a calorimeter containing 25 milliliters of water. What's the specific heat of lead if the temperature of the water rises from 25 to 26 degrees Celsius? So not a big specific heat on the lead. You find water will be much bigger than most metals. So let's look at the temperature change, 26, 25, or 1 degree Celsius. But the hot metal has got to go down to the final temperature of the water, so it's going to be 26 minus 100, which is a negative 74. What we're going to use is the idea that the heat gained by the water is equal to the heat lost by the metal, except the opposite direction. So we throw in a negative sign to account for that opposite direction. So then we can substitute and say that MC delta T for the water is equal to negative the MC delta T for the lead. What we want to solve for is the specific heat of the lead, so solving that, the specific heat of the lead is the mass times the specific heat times change temperature of the water divided by the negative mass of the lead and the change temperature of the lead. Then it's just plug and chug. 25 grams times 4.184 joules per gram degree Celsius times the 1 degree Celsius minus 11.00 grams and a minus 74 degrees Celsius in the denominator. The negatives are going to cancel and leaves us with 0.13 joules per gram degree Celsius. And you can see that that specific heat is much less than that of the water, which is why the water changes by much less than the metal changes. This has been a brief tutorial on heat and constant pressure calorimetry.